Welcome everyone to the 12th week of the higher categories reading seminar. So this is the 11th talk. So today our speaker is Vaibhav. He'll be talking about invertible natural transformations and infinity categories as fibrant objects. That is basically the third chapter of Cisinski. So okay, Vaibhav, take it away.
Okay. So I finally got a tablet, so you guys can see my tablet writing. So first, let's just recall. I think Heiko talked about this, Joel's lifting theorem.
Yeah, that's right.
So let's just recall what this is. Let P be an inner vibration between infinity categories, and given a horn, like a, maybe you might call it a left horn, for one of these connects, such that the first edge is invertible. So, in other words, you take this edge sitting inside of here, and this factors through this is just the simplicial set that has two isomorphisms, right? Or one isomorphism. So then, given such a thing, that the first thing is invertible, then there's the left. Okay. Right, so this should be familiar. We saw this already. But then one of the first things that you can read in Joel's paper, it's called complexes, and I think it's called complexes and quasi-categories. It's a short paper and it's really easy to read. So, but I guess the first thing he does really is show that complexes are the same thing as infinity groupoids, which are infinity categories where everything is invertible. Right, so let's just recall. So this says any horn fills, and this says every edge is invertible. I guess plus inner horn filling. Right. So I'm not going to go into the proof because it's not super complicated. Well, maybe I will just quickly. So going this direction, if you have X that's a complex and you want to show it's an infinity groupoid, then you can show inverses by solving appropriate horn filling problems. Right, and then the backwards direction is the one that uses Joyel's theorem. Okay, you can read that. It's not too difficult. Right, so this is one of the first kind of things that one might want to show, that if you want to translate what I guess Cisinski would call the semantics of category theory into infinity category theory. This was what Joyal's whole thing was, right? When they were first introduced in the Boardman and Vogt book as weak Hahn complexes, they didn't really necessarily have an idea that this should port ordinary category theory. And Joyal was like, maybe I can use this to make categories or to do some sort of category theory. And this is why he changed the name, right, to quasi-categories in the first place. And so this is one of the first steps one might want to talk about, is that if quasi-categories should behave like categories, then Hahn complexes should behave like groupoids or infinity groupoids. So that was one of the first things he wanted to show, and this is what he wanted to show. And I guess he actually delayed publishing all this because he wanted to show some other stuff or something. I don't know, I was reading about what he was talking about, his papers, but you can find it and put it on the website later. But okay, so let groupoid be the category of small groupoids. Subcategory of categories. Then there are adjoints. Not the inclusion. Then there's an adjoint here. Or in the book it's pi1. There's an adjoint here that I will call this, or in the book it's called that. And these are adjoints like this. So what these are is group voidify of a category C is just it's the category where you take all Hahns in C and invert them. And that forms a groupoid, right? And then this guy, the core, is the subcategory of C that just takes all the equivalences. And I guess the reason in Cisinski calls it K of this thing is that just called core, that you can show that this thing is the largest groupoid that sits inside of this category, right? So given a category C, this core is the largest groupoid that sits inside of this, and obviously in infinity land, that's translates to Hahn complexes. So, but we'll see that shortly. Then can extend this to infinity land. So let's see the quasi-category. And pull back of simplicial sets. Get this. We have the nerve of the core. You take the homotopy category, and then you take the core of that guy, and then you take the nerve of that to form a simplicial set, to form a infinity category. On this side, you take the nerve of just that. This is the whatever map that is, unit or co-unit. Get them mixed up. Take a pullback and lock this guy. And then so similarly, there's an adjunction where we have Hahn complexes that sit inside quasi-categories. And as we talked about, these are the same as infinity groupoids. And then there's taking the core forms a right adjoint. Okay, so in particular, the core is the largest complex living inside a category, infinity category C. Yeah. I think it's maximum infinity group wave. Okay, maybe I'll just pause for a sec. So this section, I might not go deeply into the proofs because I want to focus more on the next one where we show that the Joyal model structure and all that. But this proposition. So given a left or right vibration, and given a left-right vibration, if Y is a complex, then so is X. And P is a con vibration. So left or right vibrations are those that are inner vibrations, but they also lift against left horns. Right, and then a con vibration is one that lifts against all. All. Okay, so yeah. Anyway, you can show if you only have left horns, then if this guy is a con complex, then you can lift all horns. So let me quickly maybe see the proofs of a left or right vibration is conservative, and conservative just means that informally it lifts equivalences. So P of F is invertible. P of F is invertible in Y, then F is invertible in X. And I think this is that in the book. And then you can show that this implies that X is a con complex. Because anything is an equivalence at Y, right? Because that's a con complex. We want to lift any horn. So when n is greater than or equals 2, can to Yale's theorem and the fact that X is a complex. And then when n is equal to 1, what do we have? So we have some object X, and we have that it P of X, or Y. We have this guy's an equivalence in Y, and so we want there to exist something like this, such that it's this image, or the image of this is this guy, and then the image of this guy is this edge. And this guy is an equivalence in Y. Since it's a complex. And right vibrations between infinity categories are isofibrations. And an isofibration says exactly this, that you can lift such things. You can lift such equivalences where your target is lifted. Okay. Okay, now in particular, given a left to right vibration for any object Y, fiber XY, which I'll define as a pullback like this. Is a complex. So that just uses the previous proposition on this map. If this guy is a left-right vibration, then this guy is, and then you can show this. Lifts all horns. So definition, let A be a simplicial set and X be an infinity category, and equal, how do I want to write this? Constant simplicial set of objects. Okay. Find this thing as a pullback where, oh right, so given simplicial sets, I'm going to write underline hom to be a function complex. Sometimes people call it. This is also a simplicial set of maps between X and Y. Right? If anyone needs me to remind me what that is, then I can remind you. But so you take the HOMs from the simplicial set into X, and also when Y is an infinity category, then this guy is an infinity category. Okay. So you take this guy's an infinity category, and then you can take its core, as we talked about earlier. This guy sits inside of function complex from this constant to this, and then this map, at least by restricting. And this guy sits inside of it. So to find that, I'll pull back up simplicial sets, and you can spell that out a little bit. So K level 0 is functors. Not maps, simplicial sets. Level 1, it's natural transformations. Such that for any object, the component map is invertible. So these are, you can think of them as pointwise invertible. So the complex, at least whose edges are pointwise invertible in natural transformations. This is what I mean by pointwise invertible. So notice we have an inclusion. Oops. Obviously, you take the core of this guy. These are natural transformations which are invertible in the usual sense. This guy sits inside of this guy, since invertible natural transformations are pointwise invertible. But actually, they're both equal. So a natural transformation between functors like this is invertible if and only if it's pointwise invertible. Okay, so in other words, this is an if and only if. So this is the main kind of proof of this section. But more generally, for an isofibration, monomorphism. Isofibration between categories and monomorphism of simplicial sets. Then there's inequality. This is just the more general version of this statement. Y. Then there's an disequality, right? Okay, I'm not going to go into the proof of this because it takes the whole section, and as I said, I want to focus on other ones. So I'll let you do that. It's not super crazy. It just involves some playing with simplices and stuff. But this is kind of the main application of this more general statement. Okay. Let me pause there maybe. And then there's another kind of related construction, which I think shows up just briefly, but let's talk about it. There's simplicial set A and quasi-category X. Define this guy to be a simplicial set, so it's to live inside this function complex, and whose nth level is so you can associate maps in this function complex. Level n are maps like this. And then these correspond to maps from this into this function complex by like Cartesian closedness of simplicial sets, right? So we can associate simplices in this guy with such maps, and then it's such maps that factor as factors like this. So this guy has this Ka, sorry. To the inside of it, and then we say that this should factor to this guy. So informally, we can kind of think these as what I keep saying factors. So functors that invert everything from this source guy. Okay, and so when A is equal to J, we have this is just equal to this function complex. And when A is equal to this guy, this function complex, which is just X. Okay, and then there's a similar property to that earlier one where given iso vibration, infinity categories. Monodon extension. There's a trivial vibration like this. That's not going to proof for that either. That's the first section I wanted to talk about. Okay, let's go to the actually interesting one. .6 is infinity categories as fibrant objects. Okay, so let's recall Joyal's model structure. So the weak equivalences are what are called weak categorical equivalences. Right, just to remind us what that is that I have such a thing of simple sets such that for any quasi-category there's a map. Well, if we have such a thing, then for any quasi-category there's a map formed by pulling back T to C equals star S to C. And then one can take connected components of these guys and so we have this, and then we require that this should be a bijection. They're just sets. If you think of yeah, anyway, that's what a weak categorical equivalence is. And then vibrations are just monomorphisms. And then vibrations, well, a priori, we just know that vibrations include iso vibrations. But we'll show that these are actually equal. Okay. Iso vibrations, again, just to remind ourselves. You have the equivalence in Y. The source is some guy in X, then you want such a look like this. Okay. Oh, yeah. I guess I should note in Cisinski, isofibrations are defined as inner fibrations with such a property, but then sometimes isofibrations, people don't put this inner fibration part as part of the definition. They'll just say isofibrations, only the lifting property. So just be careful wherever you read this from. I think Lurie will write like this. Cisinski includes that as part of his definition. So most other places I think use this, but when I say isofibrations, I mean they are also inner fibrations. Okay, and the whole point of considering such a thing was, we'll compare it to the canonical model structure. It's actually, you were just in that category fest talk, right? He was talking about this, or he was talking about model structures on quasi-categories and whatever. So the canonical model structure on the category of categories, where weak equivalences are weak equivalences of category, or sorry, doesn't make sense, equivalences of categories. Cofibrations are functors that are injective on objects. And fibrations are ordinary isofibrations. So it satisfies a similar ordinary isofibrations. Satisfy a similar lifting thing as this. And then you don't have to worry about inner lifting conditions or whatever, because all functors of ordinary categories will, by definition, satisfy an analogous thing. So first theorem is that a simplicial set is vibrant in this model structure if and only if it's the category. And as I said, fibrations in this model structure are precisely isofibrations. In Cisinski sense, so they're inner fibrations and isofibrations. And if you guys are looking for alternate, I couldn't find actually Joyel's proof of any of these, so if you want to look up in higher typist theory over here. So you can actually show, he shows this separately than this, and he shows this just before he shows this, but you can actually just show this and then this will be a corollary. 20 minutes. Maybe we'll not go into the proof of this. It's too crazy. Yeah, maybe I'll just include the proof later, but I won't go into it right now. But it's not too yeah, not too crazy to show. So if you want to show like the forward direction of if X is fibrant, then it's an infinity category, then you can show that X is fibrant, then you want to show that this thing is this is an isofibration, and then you can show that this implies the horn filling that you need. And then the other direction you can use, there's like some condition of X is an infinity category if and only if there's a trivial fibration or you restrict to these horns. And that comes from like composition, right? And uniqueness of composition up to homotopy. And then you can show that this, and then there's one other condition that you need to show that shows that such a thing is fibrant in that model structure. But anyway, it's not too crazy to talk about, but just running out of time. So this class of weak equivalences, call it Joel, is the smallest class maps satisfying two out of three any inner anodyne extension. So contained and the trivial vibration between the categories is in this guy. Okay. So a corollary of this is that a functor between any categories is a equivalence of infinity categories. And what that means is there exists a inverse and invertible natural transformations from this to so such thing is an equivalence of infinity categories if and only if it's a equivalence. Sorry. A weak categorical equivalence. So what we already talked about that means. Okay. Sorry, I'm just trying to see what is worth talking about and what is worth skipping. So maybe we'll just make this a last remark. So invertible natural transformations are invertible edges. We're talking about these. I'm talking about these invertible natural transformations in functor categories, right? And i.e. edges that factor through J. And then one can show that, in other words, two maps of simplicious sets are related by invertible natural transformations. Right. So such things, we have a another thing like this. So Homs from J into Homs, well, Homs XY. It's the same as Homs from J times X into Y by, this is like by Cartesian closeness or whatever. And so you can show this implies that two maps of simplicious sets are related by invertible natural transformations in this way, if and only if they're J homotopic, right? They're related by like a homotopy like this. In other words, particular equivalences of infinity categories which involve such invertible natural transformations are J homotopy equivalences. Which, by the way, we constructed Joyal's model structure, it was quite a while ago, are weak equivalences in this. Okay, so just kind of sanity check. Okay. Big kind of theorem. Let F be a map of simplicious sets, then the following are equivalent. F is a weak categorical equivalence, i.e. a weak equivalence. For any equivalent, for any infinity category C, there's an equivalence of infinity categories. Y into C. X into C. There is an equivalence of ordinary categories between homotopic categories of these guys. For any infinity category C, there's an equivalence of infinity groupoids between, let's go, which, as we saw, this was invertible natural transformations. Okay. So maybe let me try very quickly to prove all these things. Okay. So let's do one if and only if two. So if F is a weak categorical equivalence, then by the construction of Joyal's model structure, where those weak equivalences are J homotopy equivalences, right? Then for any for any infinity category, fibrant object. Here's a bijection. And I'll say what this means. These are just maps up to J homotopy equivalence. So to J homotopy equivalence. So two maps are they're what do we call them? Equivalence classes of things that are related by J homotopy equivalences. And then by our kind of discussion above, that's the same as weak categorical equivalences. Right? Whenever these guys are infinity categories, these function complexes. Right, and then two implies one is actually not too hard, because if we have an equivalence of infinity categories, then taking connected components, and we just get an equivalence of connected components by bijection. Which means by definition that these are weak categorical equivalents. Okay, we have one implies two. Yes, this is what we'll show. One, and we have two, and I'll show two implies three, three implies one, 2 implies 4, 4 implies 1. Okay. With that. So two implies 3. So if we have an equivalence of infinity categories, then there's an equivalence of ordinary categories. Well, that's like basic because we have equivalence of infinity categories should form an equivalence of homotopy categories, right? Just taking homotopy categories. So that's easy. 3 implies 1. So if we have an equivalence of homotopy categories, then we have a bijection of objects. But objects in these guys are just connected components of these. Right, because you're associating these maps up to homotopy, like paths in this whatever in this infinity category, which means F is a categorical equivalence again by definition. Okay, so we did 2 implies 3, 3 implies 1, 2 implies 4, and 4 implies 1. Where did I write this down? Oh. So we have this equivalence. And we want to show that there's an equivalence here. We want to show that so we want KYC, KXC, but these are just cores, right? So in other words, we really want to show that this functor from simplicial sets to complexes, or sorry, yeah, preserves the equivalences. I guess maybe it should be from quasi-categories, because we don't define it for quasi-categories. But you can extend this to any simplicial set where you just take the maximal groupoid sitting inside a simplicial set. And I want to show that this guy preserves weak equivalences in this Joyal model structure. Sorry. I want to show sends weak equivalences between infinity categories to equivalences of complexes. Okay. There's a lemma called Ken Brown's lemma. We can show this is true if sends trivial vibrations to trivial vibrations, right? So we have sets. Take a trivial vibration between infinity categories here. And infinity categories are fibrant objects, right? That forms a map between cores, which is really just this restricted to the core. And this map sits in a square like this. These include right. So we want to show P, sorry, this P restricted to X is a trivial vibration, which is true if and only if the square is a pullback, right? Such an equivalence. So we want to show this guy. Well, we have this guy sits inside of this. This is so this guy is maps in X that are sent to weak equivalences in Y, right? By definition. So we want to kind of show, we'll actually just show that these are equal. So X lives inside of this because P is conservative, or P is well, any map, I guess, will do this. P sends equivalences to equivalences. And then this guy is because P is conservative. Okay. So then this guy is a trivial vibration. And so then by this guy, this Ken Brown's thing then, this sends trivial vibrations, and so since weak equivalences between infinity categories, the equivalences of complexes. Okay, and then finally, sorry, I'm over time now, but 4 implies 1. Of infinity groupoids. Forms a bijection between taking connected components of each. Too lazy to write them down. And then one can show that these things are really just maps of simplicial sets up to invertible natural transformation. So over here. And by our previous discussion, these are just J homotopy, maps up to J homotopy equivalence. means F is a weak categorical equivalence. This is by definition, and this is by that remark. Okay, so we showed everything. We showed 2 implies 4 and then 4 implies 1. Cool. Oops. Okay, and then there's a similar proposition 3 point. Whatever, 6 point, something similar proposition. But I'll let you look at that on your own. But that's all I have. Any questions or comments?
So let's thank.
Okay, I'm going to stop.
Stop the record. Yeah.
Yeah.